Welcome right back to AI Paper Slop. Today we are jumping straight into a paper called OPD-V, which is Visual On-Policy Self-Distillation with Modality-Balance. This is from researchers at NUS, LMU Munich, and Sun Yat-sen University.
It is a phenomenal piece of work.
It really is. So look, if you are building or fine-tuning multimodal large language models right now, here is the absolute core insight you need today. MLLMs have a massive bug. They suffer from modality imbalance.
Right. They're incredibly lazy.
Exactly. They rely so heavily on their text priors that they basically ignore the visual inputs you pass them. So OPD-V fixes this by using a dual teacher setup during post-training. You give a positive teacher a zoomed-in image crop, and you give a negative teacher a masked version of that exact same crop.
And by doing that, they isolate the real visual tokens.
Yeah, mathematically. By comparing the token probabilities between those two teachers, the system isolates what they call a Modality-Balance Trust Region. So it self-distills the student model only on the tokens that actually relied on visual evidence, and the results are wild.
Totally unprecedented for this size class.
Yeah, right. It boosted a Qwen 3.54 billion parameter model's accuracy from 64.3% to 80.01% across 6 benchmarks. I mean, you have a 4 billion parameter model beating 1 trillion parameter giants like Kimi K 2.6, and it drops your training time by over 30% while doing it.
It just fundamentally changes the ROI on post-training.
Yeah.
I mean, we were talking about achieving trillion parameter reasoning in a 4B model simply by forcing the parameters you already have to, actually perceive the image.
Yeah.
Rather than just auto-completing text.
And that is exactly where we need to unpack this, because if you hand an MLLM an image and a prompt, your baseline assumption as an ML engineer is that, well, the model is looking at the pixels to generate the answer.
Right, which is just false.
Right.
Under the hood, the joint conditioning is heavily, heavily skewed.
Why is that?
Well, when an MLLM generates a response, it conditions on 3 things.
Yeah.
Right? The visual input, your text instruction, and the autoregressive context, so the tokens it has already spat out.
Right.
Because the language priors built into those LLM backbones are so overwhelmingly strong from pre-training that autoregressive momentum just completely dominates generation.
It just steamrolls the vision encoder.
Exactly. The model essentially hallucinates an answer based on the phrasing of your text prompt and its own linguistic patterns, and it severely downweights the visual evidence.
I mean, I see this all the time in my own pipelines. It's sort of like a self-driving car that just ignores its live camera feeds because the GPS map says the road is straight.
That's a perfect analogy.
It's relying on its pre-programmed expectation, right? It's prior instead of the live evidence right on the bumper. And this brings up the massive flaw in how we currently do on-policy self-distillation, or OPSD.
Yeah, because standard OPSD has kind of become the default post-training method, right?
Yep.
The student model generates a response, and a detached teacher model scores it.
And researchers usually give that teacher a cheat code, basically.
Right. They give it privileged information, like a verified text hint or an ideal bounding box crop. The idea is so the teacher can provide a higher quality target distribution for the student to learn from.
But wait, if the teacher just grades the final answer without checking how the student arrived at it, it's okay, it's like a student taking an open book test, but they just guess the answer based on how the question is phrased. They never even open the textbook.
Exactly. They just guess well.
Right. And if the teacher just grades the final answer and gives them an A, the student never learns to actually open the book. If the student model is already stuck in this text-dominant hallucination loop, and the teacher gives it a high score simply because the generated text happened to match the hint,
then the distillation target is blindly reinforcing that text reliance.
Yeah.
You aren't teaching the model to look at the image at all. You're literally just teaching it to guess with higher confidence.
That is such a huge bottleneck.
It really is. The standard OPSD process is just severely limited by the model's own internal imbalance. The gradient updates don't fix the root cause of the hallucination.
But okay, as engineers, you can't optimize what you can't measure. So before we even talk about fixing it, how did the authors mathematically prove that this imbalance is even happening during generation?
They formalized it through this metric called the Modality-Balance Attention Ratio.
Okay, how does that work?
For any given generated sequence, they measure the total visual attention mass relative to the textual attention mass across all the transformer layers.
Oh, so you can actually look inside the black box.
Right, at a POO token level.
Yeah.
You can calculate the exact mathematical weight the model assigned to the image embeddings versus the text prompt embeddings.
And they manipulated this ratio, didn't they, to prove that the visual reliance is highly conditional?
They did. So they passed the model heavily masked images, And as you'd expect, the attention ratio plummeted. The model shifted almost entirely to relying on its text priors.
Because it couldn't see anything usable.
Exactly. When they passed the original unedited image, the ratio just hovered in this intermediate kind of ambiguous zone. But when they passed a tightly zoomed-in crop of just the task-relevant region,
The visual attention ratio spiked.
huge spike.
Okay, so that proves you can explicitly expose different degrees of modality imbalance just by augmenting the visual input, which leads us to the real genius here, the core architecture of OPD-V.
Right? How do we turn that dynamic into a training signal?
Exactly. How do we take the fact that a zoomed-in image forces visual attention and turn that into a supervised signal?
Well, the authors solved this by designing a three-way split for every single training sample.
3 simultaneous forward passes, right?
Yes, for any given sample, 3 forward passes happen at the exact same time on the exact same student-generated text prefix.
Okay, let's track the inputs for those 3 passes so you, the listener, can picture this. The student model gets the original image exactly as it appears in the dataset.
Standard baseline.
Right. Then we have the positive teacher, which receives a zoom-in image. So that's a crop containing only the task-relevant region. Finally, we have the negative teacher, and this one receives a mask image.
And that mask image is just the zoomed-in crop, but with a random black rectangular patch covering the critical details.
Okay, and this is where the mechanism gets so elegant. All 3 of these models are evaluating the exact same sequence of generated text, right?
Right, and the system looks at the probability distribution, specifically the logits, that the positive and negative teachers assign to the very next token the student is about to generate.
So we are mathematically isolating the value of the pixels.
Exactly. For every generated token, the system calculates the modality balance logits margin.
Which is just the log probability from the positive teacher minus the log probability from the negative teacher.
Yes, and if that margin is positive, it means the positive teacher, the one with the perfect visual crop, was much more confident in that specific token than the negative teacher, which, had the evidence blocked out.
So structurally, if the masked teacher couldn't predict the token, but the zoomed-in teacher could, we objectively know that token is visually grounded.
Right. We know for a fact it did not originate from a text prior.
And those specific visually grounded tokens, those form what the paper calls the Modality-Balance Trust Region.
And that trust region is the entire crux of OPD-V. Because in standard OPSD, you apply Jensen-Shannon divergence, or JSD, to distill the teacher's distribution into the student across the entire sequence.
But applying JSD universally pushes the student to mimic the teacher's text biases on the non-visual tokens too, right?
Exactly. But in OPD-V, the JSD distillation step is applied only to the tokens inside that trust region.
Oh, that is so smart. You're selectively updating the gradients only when you have mathematical proof that the teacher actually relied on the image.
It cuts out all the noise.
It makes total sense. But wait, if you're training a 4B or a 7B parameter model on your cluster right now, you know that full vocabulary Logit distillation is an absolute memory nightmare.
No, it's brutal on VRAM.
Right. We are talking about running 3 simultaneous forward passes and holding the logits for a 100,000 token vocabulary at every single position. Doesn't this just instantly out of memory your GPUs?
It absolutely would if you did a naive implementation. But the authors anticipated that and implemented a highly optimized top K distillation strategy.
Okay, how does that work on standard hardware?
Instead of calculating the divergence across the full vocabulary, they just set K to 100. So they only extract and evaluate the top 100 logits from the student model alongside the corresponding probabilities from the 2 teachers.
But wait, doesn't truncating the distribution mess up the softmax gradients during backprop? I mean, if you just chop off everything below the top 100, you're losing probability mass. That usually destabilizes training.
Normally, yes, which is why they implement a tail probability adjustment. All the remaining vocabulary mass outside that top 100 is pooled into a single scalar tail bucket.
Oh, I see.
Yeah, because the softmax distribution in these models is incredibly sharp. The tokens beyond the top 100 usually account for, less than 1 times 10 to the negative 13th of the cumulative probability mass.
That's functionally 0. So by tracking just the top 100 logits and a single tail bucket, you preserve the entire probability mass for backprop.
Exactly. It's virtually lossless compared to full vocab distillation, but it saves, massive amounts of memory.
It allows you to run this dual teacher setup without needing some insane enterprise cluster just to hold the gradients.
Precisely.
I do want to push back on the negative teacher design, though. Looking at the ablations in the paper, Why go to the trouble of dynamically generating a masked image patch? I would think a no-image condition would perform basically the same.
A lot of people assume that.
Yeah, why not just pass the negative teacher no image at all, let it rely purely on text priors, and compare that to the positive teacher?
It's a common intuition, but the ablation studies show a massive divergence there. If you use a no-image negative teacher, the final model accuracy drops to 72.17%. But with the mask image, it hits 80.01%.
Wait, a nearly 8% drop just from removing the image entirely.
Yeah.
But if the target evidence is missing in both conditions, why does preserving the background matter so much to the logits?
Because logits are hypersensitive to the modality context. If you completely remove the image, the negative teacher structurally shifts into a pure LLM mode.
Oh, it changes gears completely.
Right. You aren't just removing the specific visual evidence, you're changing the entire baseline distribution of the model. The mask image, on the other hand, keeps the visual pathway fully engaged.
It preserves the spatial relationships, the lighting.
Exactly. It preserves all that background context, but surgically deletes the specific critical detail.
So by holding the broader context constant, the delta between the positive and negative teacher logits is purely the value of that specific missing patch. It's like if you test someone in a completely dark room, they act fundamentally differently than if you test them in a bright room with just one single word redacted on a page. The masked image gives you a much sharper, more isolated contrast delta.
Exactly. It isolates the exact tokens that rely on the specific evidence rather than tokens that just rely on the presence of an image in general.
Okay, mathematically, isolating visual tokens with a trust region makes total sense. But in the real world, models often degrade or just behave weirdly when you start heavily manipulating their logits during post-training.
Sure.
Does this actually scale to dense, noisy data sets, or does it fall apart in practice?
It actually scales incredibly well. They ran this methodology through a gauntlet of 6 major benchmarks to test different failure modes.
Like VBench, right?
Yes, VBench is notorious because it forces the model to locate tiny targets in highly crowded, high-resolution scenes. If a model relies on text priors, it fails VBench because the visual cue is too small to overcome the language momentum.
They also tested on HRBench for native 4K and 8K resolution understanding, which is critical because traditional downsampling usually destroys the exact evidence you need to answer the prompt.
Right, and the empirical numbers across the board are definitive. The baseline WEN 3.54B model scored 64.30% on average. With the OPD-V training applied, that exact same 4B model jumped to 80.01%.
That is an absolute gain of nearly 16 percentage points purely from changing the post-training distillation process. No extra parameters added.
Done.
That is a staggering leap, and when you contextualize that 80%, you really start seeing how it disrupts the scaling laws we usually assume in ML.
You don't necessarily need more parameters if you can just teach the parameters you already have to properly process the visual embedding.
Exactly. This 4 billion parameter model outscored heavily optimized closed source models like Gemini 3.5 Flash and GPT 5.2.
And it vastly outperformed its own massive sibling. The 397 billion parameter version of Qwen 3.5 scored 77.44%. And the OPD-V 4B model completely knocked out the 1 trillion parameter Kimi K2.6 model, which landed at 72.81%.
That brings up a really crucial engineering question, actually. Is this just an artifact of the Qwen architecture?
What do you mean?
Well, Qwen 3.5 uses an early fusion architecture with a hybrid language backbone. Does this legit margin trick work if the model physically routes the pixels differently?
Oh, I see. No, it's entirely architecture agnostic. To prove this, researchers also tested OPD-V on Qwen 3VL, and Qwen 3VL uses a completely different setup. It leverages a deep stack architecture and interleave MROP.
Right, MROP being multimodal rotary position embedding, which encodes the 2D spatial layout of the image directly into the sequence rather than just flattening it.
Exactly. The way Qwen 3VL injects spatial features is fundamentally different from early fusion models. But OPD-V boosted the performance consistently across both architectures.
Because the trust region is calculated at the logit level.
Yes. It doesn't matter how the model's internal layers route the vision features. As long as the model outputs a probability distribution over vocabulary, the modality-balance logit's margin will correctly identify the visually grounded tokens.
Okay, so it's highly accurate and architecture agnostic, But normally when you see a compact model achieving massive reasoning gains like this, you kind of assume it's brute forcing the problem.
Right. You assume it's relying on incredibly long chain of thought generation, burning massive compute and inference time.
Exactly. That is the standard side effect of OPSD methods. As the self-distillation training goes on, models tend to become highly verbose. They ramble, generating 1,000 tokens of reasoning just to arrive at a one-word answer.
But OPD-V caused a massive behavioral reversal here. The data shows that response lengths actually dropped by 74.5% compared to standard OPSD.
A 75% reduction in tokens generated.
Yeah, it's wild. The average response lengths for the OPD-V model was 141 tokens. The standard OPSD model averaged 554 tokens.
So it's getting significantly smarter, beating trillion parameter models, and it's doing it in a fraction of the words.
Yes.
How does restricting the gradient updates to the trust region cause the model to stop rambling?
It comes back to those text priors we talked about. Standard models ramble because they are leaning on their linguistic momentum.
Yeah.
They're literally talking themselves through a hallucination, hoping to stumble onto the right logic.
Right.
But an OPD-V model is heavily grounded in the visual evidence right from the first token. It looks at the image, identifies the evidence, and just outputs the answer.
It gets straight to the point because it actually perceives the input rather than auto-completing text until it hits a stop token.
Exactly.
That efficiency paradox is fascinating. You get better reasoning through fewer tokens. And if you are generating 75% fewer tokens during the on-policy rollout phase, that has to translate directly to massive wall clock training reductions.
It absolutely does. Because the generated responses are so much shorter, the mean step latency during training dropped by 31.8% on the 4B model. It went from 352 seconds per step down to 240 seconds.
But wait, surely the dual teachers add pre-processing overhead. We established earlier that you have to construct masked crops and run 3 forward passes.
They do add compute, but the math still works out heavily in OPD-V's favor. Constructing the visual crops and applying those rectangular masks takes only 15.3 seconds of pre-processing time.
Okay.
In standard OPSD, trying to construct and insert verified text hints takes about 79.2 seconds. So even with 2 teachers evaluating the tokens, it is mathematically cheaper and faster to run this pipeline.
But if we are clipping distillation strictly to a trust region that only covers visual tokens, wouldn't the model's confidence spike on those specific tokens and eventually collapse?
What kind of collapse?
Like a degenerate state. I'd worry about mode collapse, where the model just outputs one-word answers and completely loses its conversational ability.
That's a really valid concern for any targeted distillation method, which is why tracking policy entropy is vital. And the authors show that throughout the training process, the policy entropy stabilizes cleanly around 0.8.
Ah, okay. An entropy of 0.8, meaning the model remains highly confident in its predictions, but still maintains a diverse enough probability distribution across the vocabulary to avoid repeating the same tokens over and over.
Precisely. The trust region consistently captures about 50% of the generated tokens throughout training. The model is still learning language structure from the remaining tokens, but the gradient updates are firmly anchored by the visual evidence.
That's great balance.
It proves the model stays active, avoids mode collapse, and continuously learns from a stable, high-quality signal.
Man, let's take a step back and look at what this means for the broader field. We have a post-training method that takes a model's own failure mode, its lazy reliance on text priors, and uses it to create a self-correcting trust region. By contrasting a visually perfect positive teacher against a visually impaired negative teacher, it forces the student model to only learn from tokens that actually relied on the image. It's more accurate, vastly less verbose, cheaper to train, and works across completely different model architectures.
And if we connect this mechanism to the bigger picture, it heavily implies a new frontier for all multimodal systems. The core logic here is that contrasting augmentations can map out a model's reliance on a specific modality.
Right.
There is no reason you couldn't apply this exact same blueprint to other modalities.
So like audio language models, you could have a positive teacher with pristine audio and a negative teacher where specific frequency bands or speech segments are masked out with white noise.
Exactly.
And then you distill only the tokens where the logits prove the model relied on the actual sound.
Or think about video language models. The positive teacher gets the raw sequential video, and the negative teacher gets temporally jumbled frames or clips with key action sequences blacked out.
That's brilliant. You mathematically force the model to actually watch the sequence of events rather than just guessing the plot based on the first frame and the text prompt.
It's a foundational blueprint for forcing AI to actually perceive reality, rather than just auto-completing it based on pre-training bias.
It really raises an important question for you, the listener, as you look at your own training runs today. How many of the multimodal systems you are building or querying right now are just cleverly disguised text guessers? And, how much performance is sitting on the table just waiting to be unlocked by simply forcing them to open their eyes?
It is definitely something to think about the next time you write a prompt for a vision model.
Thank you for joining us as we unpack this incredible research. Keep building, keep questioning, and we will see you next time on AI Paper Slop.